Away from the internal contents of the CRO, we need to learn how to deal with its interface, the screen and the controls. Thanks to modern technology, everything in the world can be detected using what is known as the sensors. These sensors can detect any change and convert it into electrical voltage. Note, nearly everything in the world can be detected using sensors. We have, for example, light sensors. They can detect light and change this into electrical voltage. The amount of voltage produced is related to the light intensity. We have also the microphone, which is a sound sensor, also the pH sensor, temperature sensor, humidity sensor, and many other sensors that can detect external factors. They change these external factors to electrical voltage. Notes: a sensor changes any external variable to electric voltage. A light sensor changes the intensity of light to electric voltage. As light intensity increases, the output voltage increases. A temperature sensor changes the temperature to electrical voltage. As the temperature increases, the output voltage increases. If we have a device that can study the change in voltage with time, then we can study anything in the world accurately. We will be able to study the changes in temperature and pressure. When movement, for example, any environmental changes will be studied easily. This device, which will study the change in voltage with time, is the CRO, the cathode ray oscilloscope. Note: the outputs of any of these sensors can be connected to the cathode ray oscilloscope. The CRO can draw a graph to study the changes in voltage on the y-axis, even the slightest changes in it, with time on the x-axis. Note: CRO gives a graphical representation of any kind of electrical signals, showing even the slightest change in voltage in short time periods or over long time periods. This is a simple diagram showing the interface of the CRO. Now let's see some uses of the CRO. The main use is to display the waveforms, for example, sound forms. If a microphone output is connected to the input of the CRO, this will draw the waveform of your voice, including sound pitch and loudness. Note number 1. Sound waveforms can be studied by connecting a microphone to the input terminal of the CRO. CRO can also draw the graphical representation of the heartbeats to be used in hospitals. A heartbeat sensor changes the pulses of the patient into electrical voltage. The CRO can draw the detected voltage as time goes, showing the number of pulses in a certain time and also the strength of the pulse. When no voltage is detected, this means no pulse. Note number 3. Time intervals between two racers. By using motion sensors on the finish line of the race, as the racer passes this line, an electrical pulse is given by those motion sensors. If these sensors are connected to a CRO, we can measure the accurate time interval between the racers. Note number 4. Graphical representation of the AC current. The most common use in education is to draw a graphical representation of an AC voltage. Another important use of the CRO is measuring voltage. Since the CRO is a sensitive device that can detect small changes in voltage even in short time intervals, so it is easier for the CRO to measure the fixed unchanged voltage. This is why a CRO can be used as a simple voltmeter. Note: since the CRO gives the value of the voltage, it can be used as a voltmeter. If we want to measure the potential difference across the bulb, for example, simply connect it in parallel to the Y inputs of the CRO as shown by the diagram. This was a short introduction on uses of CRO and dealing with the interface. In this part, we will study the main controlling buttons of the CRO. Before that, we must know that the signal or the voltage to be studied must be applied to the Y input. For example, to draw the sound waveform, the microphone output is connected to the Y input of the CRO as shown. Similarly, to study the change in humidity, The humidity sensor is applied to the Y input. Now let's have a look on the screen. The Y-axis of the graded screen represents the voltage axis, while the X-axis represents the time axis. Now the controlling buttons. The first control is the brightness button. The second main control is the voltage scale, or sometimes named the Y gain control. Also we have the time-based control, the brightness control. This adjusts the brightness and intensity of the signal on the screen. The Y gain control or the voltage scale controls the scale of the Y-axis or the voltage axis. For example, when this control is adjusted to 2 volts, this means that each division or square on the Y-axis represents 2 volts. The time base have the same significance, but to the X-axis. If the time-based control is adjusted to 10 seconds, this means that each division or each square on the X-axis represents 10 seconds. After the controls, now it's time to have some real examples to explain how to deal with different signals. Example number 1. The simplest signal is that of the DC supply. This is shown on connecting a DC battery to the CRO. Remember that the DC supply is connected to the Y inputs. What is the voltage of this battery? First, we must know that this is our zero line, which the red arrow points to. This triangle helps a lot in our calculations. The true value equals the number of squares multiplied by the scale given by the scale control. Since we are reading the voltage, so our axis is the Y-axis, which shows 4 squares above the zero line. Looking to the voltage scale control, the Y gain button, you will find that it is adjusted to 5 volts per division. This means that according to the given triangle, the true value of the voltage is the number of squares times the scale. This equals 20 volts. Example number 2. This shows a signal given by the finish line motion sensor in a race. What is the voltage of these pulses? Using our triangle, which shows that the number of squares multiplied by the scale equals the true value. Since the question is about voltage, so we will look for the height of the signal on the Y-axis. This clearly shows 2 squares high. The scale is given by the voltage scale or Y gain control, and it's 2 volts per division. We find that 2 squares multiplied by the scale 2 volts per square shows that the true value is 4 volts. A new question is, what is the time between the 2 pulses? The time between the 2 pulses shows the difference in time between the 2 racers when they reach the finish line of the race. As we are talking about time, we concern about the horizontal axis or the X-axis. It's clear that there are 4 squares separating the centers of the 2 pulses. In this case, the scale is the time-based control, which is adjusted to 10 seconds per square. This means that each square on the time axis represents 10 seconds. Applying our rule, we can easily find that by multiplying the number of squares, which is 4, by the scale, which is 10 seconds per square. This will give us the final results for the true value, 40 seconds. So the time difference between the 2 racers when they reach the finish line is 40 seconds. Now we finished 2 examples. The first one for reading the voltage on the Y-axis, and the second one is for reading the time on the X-axis. Now it's the time for a more advanced case, reading an AC signal coming from an AC supply or an AC generator. Example number 3. AC. This is shown on connecting an AC generator to the CRO. The first thing we need to read is the voltage. What is the voltage of this generator? We still need our triangle, which tells us that the squares times the scale equals the true value. The voltage of an AC signal is its amplitude from the zero to the peak of the signal. This takes 4 square on the y-axis as seen. Now by looking to the voltage scale on the Y gain control, which is adjusted to 0.5 volts per division, and applying our rule, we find that 4 squares times 0.5 volts per division equals 2 volts. This is the voltage of the signal. The second thing we can read directly from the screen is the periodic time of the signal. What is the periodic time of this generator? To read the periodic time of an AC signal, we must concentrate on only one complete wave and neglect the rest of the signal. If you remember that the x-axis is the time axis, so you must also know that the periodic time is the time taken by one wave. On the screen, one wave of this signal takes 3 squares on the x-axis. By looking to the time base, which shows the scale of the time axis, the x-axis, you will see it is adjusted to 20 milliseconds per division. And finally, by applying our rule, you can find that the true value of the periodic time is given by 3 squares times 20 milliseconds equals 60 milliseconds. If there will be further questions, we need to get rid of the millisecond. It's not our standard unit and it must be changed into seconds. What is the periodic time of this generator in seconds? To change the 60 milliseconds into seconds, simply divide 60 by 1000. This will give 0.06 seconds. A usual question that follows finding the periodic time is to find the frequency of the AC signal. Frequency equals 1 over periodic time, which is 1 over 0.06. This equals 16.7 Hz. Note that you cannot get the frequency from the periodic time in milliseconds. You must first convert it into seconds as given before. Example number 4 AC. Just for more practice on AC signals, this is shown on connecting an AC generator to the CRO. What is the voltage of this generator? We are still in the need of our triangle. As we learned before, the voltage of an AC signal is given by the amplitude of the signal from the zero to the peak. The screen shows it takes 2 squares high on the y-axis. The voltage scale on the Y gain button is adjusted to 2 volts per division. Applying the rule, you can see that 2 squares times 2 volts per division equals 4 volts. Now, what is the periodic time of this generator? Remember, we will concentrate on one wave and neglect the rest of the signal. One wave takes 8 squares on the x-axis. The time base, which controls the scale of the x-axis, is adjusted to 0.5 seconds per division. This means the periodic time is 8 squares times 0.5 seconds per division equals 4 seconds. After that, we will calculate the frequency the same way as previous. Frequency equals 1 over periodic time. This means 1 over 4 equals 0.25 Hz. Note that we did not make any changes to the periodic time because it's directly given in seconds, not in milliseconds like the previous example.